Okay, good morning, everyone. Top hat code for today is okay. I'm going to share my screen. And we're actually going to do two topics today. First topic is order statistics, and I think we will have a lot of time. So we will then do numerical algorithms. All right, so the first question that we're going to answer is, what do we mean by order statistics? What's going on here? So order statistics has to do with if we were to order the data, right? What would be the minimum? What would be the maximum? What would be the median? What would be the 25th percentile? What would be the 75th percentile? Right, so questions like that, okay, that's what we mean by order statistics. Now, there are two ways to do it. One way to do it is to just sort the data, and then it's usually easy to find the minimum. How do you find the minimum?
Look at the lowest one.
You look at the last position, and how would you find the maximum?
Look at the first position.
You look in the last position, and how would you find the median? Median is the 50th percentile. How would you find the median?
We had to add them all up and then divide by the number of elements.
No, that's the average. How would you find the median? The median is the middlemost element, right? So you look in position. If there are n elements, you look in position n over 2. You might need to round that up or down. Okay, and that's what we do. Okay, so this has a lot to do with sorting. That's why we usually talk about order statistics right after we talk about sorting. All right, for two reasons. First of all, if you sorted the data, then the answer would be easy. So that's one way it's related to sorting. The second way that it's related to sorting is that one way to solve this problem without sorting the data is to partially sort the data, or to do other things to the data similar to what we do in sorting algorithms. All right, so that's another strategy for solving this problem. So again, what do we mean by an order statistic? The first order statistic is the same as the minimum. It means the first position if the array were sorted. What is the nth order statistic? That's the same as the maximum. The n over 2 order statistic is the median, or 50th percentile. N over 4 is the 25th percentile. 3n over 4 is the 75th percentile, right? So again, what we're trying to do is we're trying to figure out, how do I find a sort of a relative, value without actually having to sort all the data. Right, so before we do that, we're going to look at some more specific examples, right? How do I find the max and the min? Okay, so we're going to look at a few different approaches. Okay, so this is a very sort of representative code of finding the min, right? We look at the first element in the array, we look at each additional element, and we see if the newest element, the next element is smaller than what we have, and eventually get the last one. By the way, for those who use Python, is there a easier way to get the smallest number in array? So you could just call min. You could just call min or max on a list, and you can get it that way. The problem is you don't really see what's happening behind the scenes. So a lot of programming languages have functionality, but you don't really get to see the work that is being done behind the scenes. So the way you find min is you need to keep looking at all the elements and compare them to the smallest min so far. All right, so that's the min. And can someone tell me, by looking at this, what the time complexity is of this algorithm?
O of n.
It's O of n. And we want to be more specific. We could say it's actually n minus 1 comparisons. Why is it n minus 1 and not n?
And we always have to compare one less. Like there's only one element, we'd have to compare.
Right, so we don't need to compare the first element. The first element we just assume is the min until we find something that's less than it. Same thing for the max. All right, what would you do if you needed to find the min and the max?
I mean, you can run through one loop of it and just keep track of one variable for the minimum, one variable for the maximum.
Okay, we could. That would actually probably not save too much time, but it would work. It would work. Well, here's another trick you can do. The trick you can do is you can say if it's less than the min, then update the min. Otherwise, check if it's bigger than the max. In other words, it's never going to be less than the min and bigger than the max. So we can cut down on approximately 50% of the comparisons for the max by building it in with the min. We'll come back to that in a moment. But here is a recursive approach, right? So we say if we don't need those parentheses really, but we say if n equals 0, if there's only one element, just return the first element. Otherwise, get the min of the last element and everything else. Okay, this is an example of decrease and conquer by 1. What does decrease and conquer mean? It means that each time we do reduce the size of the problem, in this case, it's decrease and conquer by 1. I should actually change the name of that. It's actually decrease. Proper way to say this is it's a decrease by 1 and conquer. That's actually a better way to say it. Okay, but its time complexity is actually no better than the iterative approach. And if it's not better, it's actually going to be worse. Why is a recursive approach worse? Because now you have the recursion stack, right, to keep track of as well. We saw that yesterday when we were talking about quicksort, and we looked at that chart at the end of the slides, and we saw that the time complexity was log of n. I said, where did that log of n come from? And the answer is there was a stack involved in keeping track of what all the partitions are. So recursion actually has a certain cost associated with it beyond the cost of just doing the work. All right. So here is finding the min and, okay, here's a recursive approach. Okay, how is this different than the one on the previous page? All right. All right, just got to fix this here. Okay, let's go back. Okay, how is this different? This is also recursive. It's also finding the min. How is this different than the previous page?
We have a mid here.
Both are using min. What? Oh, a mid. Yeah,
Mid.
but what are we doing differently? How would you describe what's being done differently? Okay, in the previous example, how much of the problem are we getting rid of at each step?
One element.
One. What are we doing here? We're breaking the problem into 2 equal parts, right? We're solving each subpart, and then we're getting the min of those 2. Okay, so this is actually divide and conquer. Okay, the recurrence would look like this, right? We have 1 plus 2 times, right, the 2 subproblems. Each subproblem is half the size. We use our master theorem. So in the master theorem, we have A is the multiple, that's 2. B is what you divide by. And then C is the power of n. So 1 is n to the 0, so C is 0. So we have case 2 of the master theorem. And so we get, sorry, this is not case 2. This is, I think it's case 1, actually. So we get n to the log 2 of 2. Which is n to the 1, which is over n. So we don't gain anything. Okay, so all 3 of these, the linear approach, the decrease by 1 and conquer approach, and the divide and conquer approach all have the same time complexity. I'm just doing that to show you different ways to do it. All right, as I mentioned before, we can get a slight improvement if we do the min and max simultaneously. So notice what we're doing here. We're saying if it's less than the min, update the min. Otherwise, maybe it's bigger than the max. But if it's less than the min, it's not going to be also bigger than the max. All right. So in the worst case, we will always have to do both comparisons for every element. So the number of comparisons is 2 times n minus 1. In the best case, we will only have to do one comparison per iteration. So we get n minus 1. On average, we're going to have to do one comparison here because we always have to do an if, and about 50% of the time we're going to have to do this. That's where this 3/2 times n minus 1 comes from. Okay, so instead of it being roughly 2n or 2 times n minus 1, we get it down to 1.5n, which is better, still O of n. Now we get to the more general problem, right? So the more general problem is the ith order statistic. I don't just want a min, I just want max. I want to get the 20 percentile, the 40 percentile, the 50th percentile. What do I do? Right? So we have a few strategies listed here. Okay, one strategy is to sort the data. Right? If we need to sort the data, the question is, okay, so which sort do I use? Any suggestions? So if you had a choice, right? We stopped the lecture right here, and I said, which sort would you use for this kind of problem? What would you use? So more generally, right? You're working on that assignment now, assignment number 2 with the sorting. So what have you discovered, or based on the analysis we did in lectures 1 and 3 and 4, right? Which sort would you recommend if we need to sort some data?
Merge sort,
Okay, why do you say that?
because that's n log n always.
Okay, it's n log n always, so that's a pretty good candidate. Okay, quick sort is good because it's got a good average case, even better than the merge sort. It doesn't have the overhead, right? The overhead of the auxiliary storage. So those are, those are reasonable answers. What would happen if I told you that the data was finite precision, that all the numbers were, let's say these were exam scores, and all the numbers are between 1 and 100? So based on yesterday's lecture, what would you recommend?
Radix sort.
So you might do a counting sort or a radix sort, right? Because those are linear time sorts. Okay, let's move on to the next bullet. So what happens if I don't really need to sort all the data. I just want to know, the top 20%, right? The top 20% are going to make Dean's list. Okay, so I don't need to do a full sort. What am I going to do? So what we do is we look at a sort that keeps finding the mins or the maxes, right? Which kind of sorts do that? So it says here, selection sort does that, right? It keeps finding the min, the next min. Bubble sort finds the heaviest one or the lightest one, depending on how you write it. Heap sort also, right? It always has the min on the top. Why is insertion sort not listed here? Why doesn't it work like that? Does insertion sort keep finding the next min? What do you say?
I think it's just finding the place to insert.
It's finding the place to insert. So the first position on the left part of the array in insertion sort is not necessarily the smallest. Not until the very end can you guarantee that it's the smallest, right? Okay, so you have to understand the sorts to figure out which one would work partially, right? So if I only do, let's say, I need the top 20%, so I run 20% of the bubble sort, 20% of the selection sort, 20% of the heap sort, and I will now have the top 20% or the lowest 20%, depending on what I want. All right, I have a note here. It says considerations about the relative value of I. Why? So if I want to find I equals 1, I want to find the minimum, so I'm going to code my selection sort or my bubble sort or my heap sort to use a min heap, or to you bubble sort so that I get the smallest first, so I get the smallest in the selection sort. If I need I equals, the last thing, or the second to last, or the third to last, I'm going to code my algorithms. I'm going to use a max heap. I'm going to use a selection sort that finds the maxes, right? So you have to pay attention to what the I is. If the I is closer to 1, you're going to code it one way. If the I is closer to the other, you're going to code it the other way. So you have to be mindful of that. Okay, now we get to a quick select. Okay, so quick select, I actually have the code for it here. Came from the Geeks for Geeks. And does this remind you of anything? And you can look at the name or you can look at the code. It should remind you of something. There are a few hints here. Look at the name, look at the comments, look at the code. Which one?
Quick sort.
It should remind you of quicksort. That's why it's called quick select. That's why the comment says to use the partition algorithm from quicksort, because they overlap. All right, so take a look at the code here and tell me in what significant way is it different than quicksort? There's a major difference here. I'm not talking about little differences, a major difference here. Okay, so a minor difference is, okay, we're returning a position, right? We're not returning an array, but that's secondary. Okay, take a look at this. Look at these lines of code here. Okay, so obviously this is on the left side, right? This is everything on the left side of the K is the pivot, right? Sorry, index is the pivot. So this is everything up to the index. This is everything after the index. Now, in quicksort, which side do we do? Do we do the left side or the right side? When we do the recursion, do we do the left or the right? No one here understands how quicksort works?
Wait, couldn't it be either, depending how you want to do it?
Well, I'm saying if you're writing a recursive version of quicksort, which is how it's usually done. So which side do we iterate on? The left side or the right side? We find a pivot, right? We use partition to find pivot. We put all the smaller elements on the left, all the larger elements on the right, and then we do recursion. So which side do we do recursion on? The left side or the right side? The answer is both, right? You can't just sort one side in quicksort. You got to do the left side and the right side. So hopefully either you just didn't understand my question or you're being shy, but you need to understand that, right? Quicksort sorts the left and it sorts the right. Okay, with that in mind, tell me, what does quick select do? Does it do the left side or the right side?
It's doing both.
It does one or the other, okay? That's the difference. Quicksort always has to do the left and the right. This does one or the other. Everyone see? If, else, one or the other. Okay, which one does it do? Well, it figures out which side has it. So let's say I take my data and I organize it into two groups, the smaller group and the larger group. Okay, when I say small, I don't mean smaller in the number of people, but smaller sizes. I take my test scores, right? So anyone who got less than a 60, I put in one pile, and anyone who got more than a 60 goes in the other pile, right? And I want to find the top 10 scores. Which side am I going to look at? The ones less than 60 or the ones greater than 60?
Assumably greater than 60, wouldn't you have to
Ones that
know?
are greater than 60. So that's what this code is saying. It's saying figure out which side of the data, which of the two piles, which of the two sides of the array is my kth smallest going to be in, and that's where I'm going to look. So that's the major difference between this and quicksort. In quicksort, I have to process the left and the right. It's divide and conquer with uneven sizes because the left and right aren't necessarily the same. It's not like merge sort, but I have to do both sides. This is decrease and conquer, right? I'm breaking up the problem with variable size, but I only have to do one side or the other, right? Everyone get that? I'm doing one side or the other, which means it's going to be faster than quicksort. So we're going to here, let's do some analysis here. In the worst case, what happens? All the data is on one side. Okay, we saw this with quicksort as well. And so now, how much did my problem go down? It went down by one element. So the work that needs to be done is O of n squared. That's a worst case analysis. In the best case, what happens? Okay, in the best case, Basically, it's nice and even. Okay. It's, the thing is perfectly in the middle, and that's good. All right. What do I mean by decent case? Decent case means, it's more or less in the middle, right? So if it's more or less in the middle, how much work did I need to do to figure, to get half of the data on one side, half on the other, n-1, and then I only need to do one of the sub problems, so that's O of n. All right. How do we know it's O of n? Because A equals 1 if I use my master theorem, B equals 2, C equals 1, and I use the master theorem to get me that. Now comes the hard part. Okay, if you thought the recurrence we did yesterday was bad, this is worse. Okay, so we find an average. So some of this is similar to what we did yesterday, right? You divide everything by n, and we need to iterate over all possible positions. And why are we taking the max? Because we're going to assume the worst of it, right? We're going to assume that it's always on the bigger side. Okay, now it turns out that the solution to this recurrence, we're not going to solve this recurrence, but it turns out that the solution to this recurrence is O of n. Okay, so let me summarize what we have so far here. The worst case of this quick select is n squared. In best case, it's O of n. And in the average case, it's also O of n. So that's pretty good, right? We can find the not only the min and the max, but any percentile in O of n times. The problem is the worst case. Okay, we don't really like a worst case of n squared. Why is that bad? How do we know that's pretty bad? Could I easily do better than that in a worst case? So if I would have sorted, I think Ellie mentioned before, if I would have sorted, right, with merge sort, I could have done it in n log n. I could have used heap sort and done it in n log n. So I could have sorted the whole data and in worst case n log n, and I could have gotten my answer. So getting a worst case for the selection problem, for the order statistic problem of n squared is pretty bad. So the question is there another approach we can use? And the answer is there is. Okay, this is one of the most, it's not such a big algorithm, but it's one of the most sort of technically difficult algorithms of the whole course. All right, so let me explain the basic idea first. The basic idea is to break up your data into little pieces, and we find the median of each of those pieces. Okay, so the pieces are in chunks of 5 data elements, and we take those medians. Okay, what does it mean to be the median of 5 elements? Can someone answer that?
It was ordered to the third element.
That's correct. Okay, so if I were to sort those 5 elements, which I'm not going to do, but if I were to sort those 5 elements and I find the median of those 5, so it would be the third in the sorted list. So that's what I'm doing. I'm taking all my data, my n elements, breaking them up into these chunks of 5 each, find the median of both, and then I take the median of all those medians in a recursive kind of approach. Now, I'm just going to jump ahead here. So how do I get the median of the 5? Okay, so Ellie just said if you were to sort it, right, it would be the third thing. And how long does it take to sort 5 elements? So there are a lot of things we could do here, right? We could look at all of them, look at all the possibilities. Okay, so that's not really such a good idea. But if we sort it using insertion sort, so remember how long insertion sort takes. If it's n elements, it takes n times n minus 1 divided by 2. So if I were to use insertion sort on 5 elements, it'd be 5 times 4 divided by 2 is 10 comparisons. So it takes 10 comparisons using insertion sort to find the median of 5. However, and I don't have the exact code for it here, but you can click on these links if you want. You can actually do better. You can get it in 7 comparisons or even in 6 comparisons. The code for it is rather complicated, but we can get it down a little bit further. All right, 5 happens to be sort of a nice number. In other words, if you take a number less than 5, it doesn't work so well. and if you take a number greater than 5. So 5 is sort of this, no pun intended, it's a happy medium for doing the medians. Okay, so that's the idea here. All right, so let's run through this as some Python code. Let's run through it together so you get a little bit of a understanding of the actual, details of it. Okay, what does this line here do? Okay, so this slices the array into chunks. It says get me, okay, the array is called A, positions J through J plus 5, not inclusive. Okay, so J, position J, not including J plus 5. So chunks of 5 for the entire array. All right, so we now have a bunch of sublists. Then we are finding the median of each of these lists. Now, this particular code, which came from a website, a good website called brilliant.org, it actually does sort the sublists. Okay, if anyone was paying attention in the last 2 lectures, what sort is it using when it calls sorted? So it's using the built-in sort, but did anyone catch what sort Python is probably using behind the scenes?
There was mix of quick sort and some other sort.
I'm sorry, I didn't catch what you said.
Remember you said it was mix of quick sort and some other sort.
Well, C uses quicksort to do its internal sort. Python uses something called TIM sort, and TIM is like a combination of insertion and merge. Okay, so in any case, this particular code is sorting those sublists of 5 each for each sublist, and then it's taking the one in position 2 out of the 5. Like position 2 is really the 3rd position, right? 0, 1, 2, 3, 4, right? So just like in Java and in C, right, we go from 0 through n-1. So that's true of Python as well. All right, so again, this is really not the best way to get the median. There are those things from that Stack Overflow, but it's a simple enough way to get it. All right, then we deal with the case if it's smaller than that. All right, so otherwise, what do? We take all these medians and we find their median. And we do this recursively, right? This is a recursive call to the same function. So we keep on finding these medians. And what are we going to be left with at the end? So when we're all done, we're going to get a median. Now, it turns out that this median that we get is not actually the real median. It's like a pseudo median. Okay, but that's why we have this code on the bottom. Okay, so what this ladder code does is it takes that median, that pivot, right, which is a very close to the median, and it uses that. And the reason we do that is, remember what our problem was over here, our worst case. When does the worst case happen? It's when our pivot is far away from the actual median. So all this work is really to get a very good estimate of the median, so that when we do our pivoting, we get, approximately half on one side, approximately half on the other, and then we use our quick select. This is really like a quick select to do the rest of the work. All right, so as with many other algorithms, the best way to understand what's really going on is to visualize it. So here's what we're going to do. This actually comes from Wikipedia, and they did a nice job of sort of visualizing what's going on. All right, so let me sort of walk you through this. Okay, what you see on the bottom is the chunks of 5. Okay, everyone see the chunks of 5? Right, we got chunks of 5 there.
Yeah.
And so these are all 100 numbers between 0 and 99. And eventually, so what do we do with those chunks of 5? Okay, we take their medians. Okay, so this row that you see there are the medians, right? And what do we do with that list? So if we're calling this recursively, what are we going to do with that? So you don't see all the iterations here, but what's going to happen with that?
Find the median of those.
You're going to find the median of those medians. And how many are going to have now? So the first time around, how many medians did you have?
10.
Well, the first time around, how many did you have?
20,
20, right? Next time around, how many are you going to have?
10,
No,
One.
4, right? Because you keep dividing by 5. Okay. And then you're going to do one more time and you're going to get 1, right? So that's this 47. Now, can someone tell me that 47, that's our median of medians after the recursion is all done. Okay. Is that the actual median?
No.
How do you know that?
not necessarily.
50.
Not necessarily. You know it isn't. Why not?
It's 50.
It should be 50, right?
But in this case, right?
49, 49, or 50, but it's not 47, right? Yes, you're on
But
the
that's-
same
yeah,
page as me. These are the numbers 0 through 99. Okay, so they, randomize them. Okay, so 47 is not the real median. So that's part of what's nice about this illustration, right? It's using something that's close, but not cigar, as the expression goes, right? Close but not cigar, right? It's not the real median. Okay, but now we use the quick select part to say that's our pivot. And if you use a pivot of 47, you're going to get nice performance at that point. So again, the purpose of the median of medians by itself is just to get you a very good estimate of the median. Once you have a very good estimate of the median, then your quick select is going to do a great job and get you the real median that you need. All right, so that's what's going on here. Yeah, question?
Yes. So we're trying to get the pivot to the middle.
So,
Of
right,
the
you can think of
range?
it that way. So think about, we had the quick select, right? In the quick select, we don't control where the pivot is, right? We might use a randomized pivot or one of the other strategies we have. It's not necessarily going to do a good job, okay? It does a pretty good job in the average case, but it does a poor job in the worst case. The idea here is to say that our median is going to be pretty darn close to the real median, and therefore our quick select. So this together with quick select is going to give us the performance we need. Now, I probably haven't convinced you yet that it's going to give you that performance. How do I know that 47 is good enough to get us the performance we need? So that's going to happen on the next slide. Did I answer your question?
Yes, Professor.
I'm sorry?
Yes, Professor.
Yes. Okay. So take a look at this. Okay. This is a little more advanced than any of the recurrences we've seen before, but it's sort of cool. Okay. And let me explain what this recurrence is. Okay. So what we're saying is, what is the time it takes, what's the operations it takes to do this median of median stuff? Okay. So you say it's bounded above. Why do we say bounded above? Because this is like an upper bound, right? Okay. By 3 things. 3 things. Okay. One thing is finding the median of the medians. Okay, now notice it doesn't say n divided by 5, right? Right, it says t of n divided by 5 because it's got to do that recursively, right? So it's taking the same problem when you take one median out of each chunk of 5 and repeating, recursively doing that, okay? So that's where this t of n divided by 5 is coming from, okay? I'm going to skip the 7n because that's the hardest part to understand here. The c of n is pretty easy to understand as well, right? We're doing quick select, okay? Quick select involves partition, right? How much work is a partition? So if you think about what we did in last class, we either said n minus 1, n, or n plus 1 is the work for doing partition, right? Because basically you're just doing comparisons to figure out whether a data element should go on the left or the right. So we basically need to run through all the elements. And then there's one more piece of work to just move the pivot into position. So it's roughly going to be 1 times n, okay? So we write c of n just to be careful, but it really, that's why I said over here, probably 1, okay? This is going to be approximately n minus 1, n plus 1. That's what this is, okay? That's the work for the partitioning and quick select. Where does this come from? Okay, this is the hardest part to understand, okay? And to do that, we need to go back to this picture here, Okay, and what we need to do is we look at these in pairs. We say, take 5 elements here and take 5 elements there and look at them as a unit of 10. And we say, how many of those 10 elements are going to be bigger than, or smaller, doesn't really matter, than the ultimate median. I'm sorry, than the median on one side. And the answer is 7. Okay, so that's what I wrote here. So let's just read this together. For every 10 elements, a pair of columns in the diagram, right? So usually one on one side and one on the other side. At least 3 will be on one side of the overall median of medians, and the other will be, so you have leaving 7. Okay, why is that true? Because we should never have, right? You should never have like, you know, all 5 here and 3 more that are all smaller than something, right? Because the ones on this side should generally be bigger and the ones on this side should generally be smaller. So the most we would ever have is 70% on one side. Now in reality, it'll probably be much closer to 50%. The most we're ever going to have is 70%. So that's where this comes from. This says, how big is the, when I do my partition, how big is one side going to be? And the answer is it's at most 70%, right? So when, again, I do my partition, I have my pivot, how much is going to be on one side of this pseudo median, this estimate of median? And the answer is at most 70%. Okay, so that explains this recurrence. And now the question is, what on earth is the solution to that recurrence? Okay, so that's not something I would expect you to be able to solve. But what we're going to do is we're going to do a proof by induction. Okay, so take a look at this. Okay, we're going to make an assumption. We're going to make an assumption that the solution to this is less than or equal to 10 times C of n. Now, the way proof by induction works is you make an assumption. This is more like a strong induction. And if everything works with that assumption, then it's good. So let's see, okay? If T of n is less than or equal to 10 times C of n, and again, C is probably 1, but we don't know that, so we're leaving it more vague, right? So we plug in, okay? So what is our n here? N is n over 5 in this case. So we plug in n over 5 for n, and we get 2C of n. In this case, we plug in 7n over 10 for n, and we get 7n over 10 times the 10 is 7C of n. C of n is just C of n, 1 times C of n. So how many C of n's do we have? 2 plus 7 plus 1 is what?
9.
10. Okay, so what did we just establish? That if T of n is less than T of C of 10 C of n, it works. It's consistent with each other, okay? So what have we shown? We've shown that the T of n in this case is bounded above by some constant multiple of n, okay? C is probably 1, but even if it's bigger, it's still linear. So it comes out that the worst case for this median of medians combined with the quick select is O of n. Okay, so that is that's median medians. Okay, anyone have any questions? Anyone want me to go over any particular aspect of this?
Professor, can you go over this analysis again?
Yeah. Okay, so there are 2 pieces to the analysis. One of them is understanding the recurrence equation, and the other is using the proof by induction, by strong induction, to show that it's bounded above by a multiple of it. So in terms of the recurrence, we're saying it's bounded above by this. Why? Because there are 3 pieces of work that need to be done. Number 1, we need to find the median of each medians. So what we do is we break it up into chunks of 5, and then we found the median of those. Right, so we're doing the same algorithm on 1/5 of the data. So that's where this comes from. We're doing the same algorithm on 1/5 of the data. The other thing is we need to do quick select. Okay, So in quick select, we do one side or the other. So we say, how much is there going to be on the side we're going to do? So the most it could be is 70%. The reason it could be the most is 70% is because for any pair of these, so you could check that, right? Look at how many are gray in any pair, okay? When I say a pair, I mean take one from this side, take one from that side. The most you have, I guess, is 6, right? The most you have is 6, right? If I take a pair, you know, from this end and from that end, and I look at the gray, which are the ones that are smaller than the pseudo median, or I look at the white, right? The most I get is I ever have is 6. Okay, so we're saying that the upper bound is 70%. At most, 70% will be on the side of the array that I need to do recursion on. And then this work here is for the partition. So as we saw in yesterday's class, partitioning usually takes n minus 1 or n plus 1 comparisons. So we're saying to be safe, we're saying it's a multiple of n, maybe 2n, 3n, but it's not going to be more than a multiple of n. Now we use induction to show what the solution is. So we say, let's assume that the this T of n is bounded by 10 times C of n. What happens? So we look at each of the 3 pieces. We say, okay, so T of n divided by 5. If I plug in n divided by 5 into here, I get 10c n divided by 5. That comes out to be 2cn. If I plug in 7n divided by 10 into here, I get 10c, 7n over 10. The 10s cancel out, and I get 7cn. Cn is just 1 times cn. I add these 3 things up. I get 2, 7, and 1 c of n, 10cn, which is consistent with our assumption. So it sort of is internally consistent. It makes sense. So therefore, our assumption that T of n is bounded above by 10c of n works.
So the recurrence equation, do we have to memorize it by heart?
You should, you know, you would not be expected to solve this recurrence. You should, you know, you should understand that. You should understand the recurrence at this point, but you wouldn't need to like solve that using, you know, exactly.
Okay. Thank you, Professor.
So you should understand this slide, okay? You should understand.
Professor, still a question that why is the quick select part as C of n?
C times n, that third part? Well, actually, that's not the quick select, that's the partition part. This is the partition. So we said that really partition is n, either n minus 1, n, or n plus 1. But we're saying, let's say we did a sloppy implementation, right? So it's going to be C of n, you know, maybe it's C is 1 or 2 or something, it's some kind of constant. So just to be sure, you know, as an upper bound, we're going to say we're going to leave it as C rather than assume that C is 1.
So it's like worst case?
It's
worst case.
Yeah, it's kind of a worst case. It's saying, you know, we don't know what that multiple really is. We think it's 1, but even if it's bigger than that, it's still going to work. Okay. All right, so that's a little bit on order statistics. And what I'd like to do now is the second part of today's lecture. We're going to talk about numerical algorithms. All right, so our first numerical algorithm is not something you would normally find in a algorithms course. I don't know that you would even find it in any course. I first learned about it from the inventor of the Doomsday algorithm himself, a person by the name of John Conway. John Conway was a British mathematician, and later in life, he went to Princeton University, and he was a visiting professor at Queens College. I'm trying to guess when that was. I would say about 10 years ago, maybe a little more, but around 10 years ago. And he gave a lecture at Queens College on calendar algorithms. And he started with the Doomsday algorithm, and he did some other algorithms. So I was at that, and I said, this is cool. I like to teach this to my students. He died 2 years ago while I was actually, was I teaching the course? Yeah, I was teaching the course. It was the beginning of COVID, and he passed away of COVID. He died, I believe he died of COVID. So what is the Doomsday algorithm? The Doomsday algorithm is a pretty cool algorithm. It's used to mentally calculate, meaning in your head, without pen, without paper, without a calculator, what day of the week any given date is. Okay, so there are a few things you need to memorize, but once you're good at it, you could do it in your head. I actually I don't know how this happened, but my daughter in high school like overheard it, and she got used to it, and she had to teach something to her calculus class, and she did her presentation on Doomsday algorithm. Okay, she actually has a modification to the algorithm that makes it even a little easier. All right, so we're going to do some examples here, but before we do the examples, let me explain how it works. Okay, so what you need to do is you start by finding out what is the last day of February in a given year. So we all know that in a non-leap year, it's the 28th, and in a leap year, it's the 29th. But what day of the week is it? Okay, so that's the first thing we need to figure out. We call that Doomsday. Doomsday is the last day of February in a given year. So this is the part you need to memorize. Okay, you need to memorize what day of the week it was for 3 years, 1800, 1900, and 2000. And I'm going to teach you a mnemonic for that. Okay, so I don't know if the facts are correct, but mnemonics don't have to be correct. They just have to help you remember. All right, so in the 1800s, we're going to assume that people did not know about fat, and that fat gives you heart attacks and strokes and stuff like that. So they ate a lot of fried food. Okay, so that's 1800. Fried food, Friday, right? The last day of February was Friday, right? Now, the next mnemonic doesn't work anymore, but back when I started teaching this, pretty much all of my students were born in the 1900s. That's not necessarily true anymore, right? So some of you are probably born, maybe even most of you were born after the year 2000. But when I started teaching this, it was we were born in the 1900s. Okay, so again, it doesn't work for you, but if you like, you can say their parents were probably wed in the 1900s. That's probably still true for most of you. Okay, and then for 2000, we have a different mnemonic, and that is everyone heard the Y2K bug. Everyone thought the world was going to like blow up in January 1st, 2000, that all the computers were going to get messed up, and I have some stories about that. But in the end, it was no big deal, minor glitches, right? By the way, why is Doomsday the 28th of February 1800, 28th of February 1900, and 29th the February 2000? Anyone know why? So remember how it works, right? Leap years are every 4th year, unless it's a century year. If it's a century year, then it's not a leap year, unless it's divisible by 400. So 1800 is not divisible by 400. 1900 is not divisible by 400, but it is a century year. That's why it's February 28th. But 2000 is divisible by 400, so therefore it is back to being a leap year. Okay, so we're going to do some examples here. Okay, so the first example is for today. Today is July 12th, 2022. And we're going to determine what day of the week it is algorithmically. Okay, so the first thing is, what is the doomsday for the anchor year, the year 2000? So remember Y2K, right? 2000, everyone thought there was going to be a Y2K bug. So we remember Tuesday. And here's what we do. We take the 2 digits of that year, the last 2 digits of that year, the 22, and we divide by 12 and we get 1. We also take the mod divided by 12 and we get 10. And we take that 10 and divide by 4 and we get 2. When we add those up, we get 1 plus 10 plus 2 is 13. Now, what are we really trying to do here? What we're trying to do is we're trying to figure out how much has the day of the week shifted since that year. Okay, so does anyone know if I go from one year to the next? So next year, for example, what day of the week will July 12th be? Anyone know? So today, July 12th is a Tuesday, but next year it's going to be what? I'll give you a hint. How many days are there in a week?
7.
7. And how many days, how many weeks are there in a year?
52,
52. 7 times 52 is how much?
364,
364. And how many days are there in a year, not a leap year?
365.
Okay, so that means we have 52 perfect weeks and one more day in a solar year. So that means that next year, July 12th, is going to be one day later. It's going to be a Wednesday. All right. So what this is doing is it's trying to figure out how many days has Doomsday shifted from the year 2000 when we know it's on a Tuesday. All right. So this is the algorithm as it's usually published. I'm just going to show you my daughter's variation, which is a little easier. So let's just bring up. Okay, so her variation works as follows. She says take 22 and divide that by 7 is this, hold on, is that her variation? Just 1 second. Let's see if I remember this. So that's equal to 3. And then we had the 7, 22. Let's see if that's right. We have, what's that? That's 5. Okay, I don't know. I remember I gotta practice variation. But anyway, this works here. Okay, so ignore the variation for now. Okay, so what does that mean? It means that in the 22 years since the year 2000, the Doomsday has shifted by 13 days. So if Doomsday was a Tuesday in the year 2000, then in the year 2022, it's 13 days later, which is a Monday. Okay, so again, in 2000, it was the last day of February was a Tuesday. In 2001, it was a Wednesday. In 2003, it was a Thursday. In 2004, which is a leap year, it advanced 2. So it's a Friday. I'm sorry, it's a Saturday because it moved by 2, right? So what this is doing is it's saying in 22 years, how much did it advance? It advanced 13 days, which is like going to a Monday. Now, how does that help me with July? So the answer is, if you Google Doomsday algorithm, you'll find some mnemonics. You'll find many other days, right? So there are 52 days of the calendar that are also going to be the same day as Doomsday. And these are some of them. These are some ones that are easy to remember. Okay, so the mnemonic is, I work 9 to 5 at 7-Eleven. So we have 9/5, which is September 5th, 5/9, which is May 9th, July 11th, and November 7th are all going to be the same day of the week as Doomsday, which means that July 11th is also going to be a Monday. And if today is July 12th, it's one day later. So it's a Tuesday. Pretty cool, right? So you don't need a calculator. You need to remember this little algorithm here, and you need to remember the anchor years, right? For the year 2000, year 1900, and the year 1800. So let's do another example so you get the hang of this here. Okay, so this one is February 13th, 2020, which was probably a day I did this at Queens College back in that semester just before COVID. Okay, so we take our 20 divided by 12, we get 1. Do the modulo, we get 8. Take that 8 and divide it by 4, and we get 2. Okay, 1 plus 8 plus 2 is 11. So what does that mean? It means that Doomsday, February 29th, 2020, was 11 days after the Doomsday of the year 2000. Okay, so that's a Saturday. Is that right? Yeah. Because it's a week later plus 4 days later is Saturday. Okay, so once again, we use the same mnemonic. Okay. But in this case, we're not actually going to use the mnemonic. Okay, we're going to say February 13th is 16 days before the doomsday. Right, so 16 days before the doomsday is 2 weeks before the doomsday, which is a Saturday. And 2 days before that, right, to get us to the 16 days is a Thursday. So we conclude that February 13th, 2020 is a Thursday. All right, so one more example. Okay, what's the significance of this date? Anybody? As the 100th anniversary of the United States of America. Okay, so let's do that. So we take our 76 divided by 12 as a integer quotient of 6. 76 mod 12 has an integer remainder of 4. And you take that 4 and divide by 4, you get 1. So 6 plus 4 plus 1 is 11. Okay, the doomsday for anchor year 1800. Again, the 1800s is when people ate too much fried food. So it's Friday. 11 days later, so 7 days after Friday is Friday. 4 more days is Saturday, Sunday, Monday, Tuesday. So that means February 29th, 1876 is a Tuesday. And we want something that's near July 4th. So July 11th is near July 4th. 7 days before July 11th is July 4th. So that means it's also going to be a Tuesday. So July 4th, 1876 is a Tuesday. So the next time you go to a party, you can impress them with your knowledge. Okay. So if you want to figure out when someone was born, you know, what day of the week they were born, you can do that and you don't need to go to Google. Any questions about that? All right. Our next numerical algorithm is big integer multiplication. So even though doomsday is not usually taught in analysis of algorithms class, big integer multiplication is a classic example of divide and conquer. Okay, so what we do is we start with the traditional grade school algorithm. So at some point in elementary school, you learn how to multiply numbers that were too big to memorize from your multiplication tables, right? So can someone tell us if you have a 5-digit number and you need to multiply it by a 5-digit number, what do you do? Before calculators or without calculators, without Google? Anyone go to elementary school here?
Just add them up that many times.
What do?
You add 5 to whatever you're multiplying it by that many times.
I'm saying you have a 5-digit number and you need to multiply by a 5-digit number. So how do we solve that? Right. So you want me to bring up a notepad?
By the first digit, then add a 0.
Okay, there we go. That's what I want to get, right? So if I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and I need to multiply that by 6, 7, 8, 9, 0. So what do? I multiply the 0 by 1, 2, 3, 4, 5. And then I'm going to multiply 9 by 1, 2, 3, 4, 5. And then I multiply that by a 10 because I have to shift everything, right? Then I'm going to multiply 8 by 1, 2, 3, 4, 5, and I multiply that by 100 to shift it. And then I multiply 7. Everyone get the idea here? 7 times 1, 2, 3, 4, 5, and I multiply that by 1,000. And then I do 6 times 1, 2, 3, 4, 5, and I multiply that by 10,000. Okay, maybe I'll put this example in the slides so we all have it. Okay, I'll make a How to get all these spaces in there? Okay, so let's say, compute. Okay, so I gotta find all of these. Okay. And then we add these up, right? Add them up to get final product. Okay, so in notational terms, what are we doing here? Right, we take our rightmost digit and we multiply it by all the digits in X. Then we take the next digit, Y2, we multiply it by all the digits in X and the big X. Then we take Y3, multiply by all the digits in X. So how much work is being done in terms of multiplications? So let's break it down. How much work is being done? How many multiplications when I take this Y1 and multiply it by all these X's, little X's? N, right? Because I have N digits here, multiplying it by this one thing, so that's N. Now, if I need to do that, not just for one Y, but for the whole thing, how much work is being done?
N squared, the same
N
length.
squared, N squared. Okay, that's just multiplications. There are some additions that are taking place as well, but the additions are cheaper operations than multiplications, right? Does that make sense? Right, multiplication, there's more involved in multiplication than addition, so we don't really care about the additions so much. Okay. All right, so what we're going to do now is we're going to do a divide and conquer approach. Who can remind us what divide and conquer is? For example, merge sort, quick sort, stooge sort. Those are all divide and conquer.
Smaller sections and then solve.
Okay, right. So you divide the problem into smaller subproblems, you solve each subproblem, and then you put the solutions back together. So what we're going to do is we're going to take the following. We're going to take our Y and divide it into rightmost digits and leftmost digits. Same for the X. Leftmost digits, rightmost digits, and we're going to cross multiply. We're going to multiply all the digits on the right by the digits on the left, the digits on the right by the digits on the right over here. And then we take these digits on the left multiplied by the ones on the left and the right. So what you can think of it like this. Okay, so look at this bullet point here. We're saying X times Y is like taking the left part of X times the right part of the left part of Y, the proper amount of shifting, right? Because you can't forget that there are, implicit zeros there. You take the left part of X and the right part of Y. You take the X part, the left part of Y and the right part of X, and then the right part of X and the right part of Y. Okay, so that's what we're doing over there. So we have 4 subproblems, and each is half the size. Why are they each half the size? Everyone see the 4 subproblems? Here's one subproblem. There's another subproblem, another subproblem, another subproblem. So we have 4 subproblems. Why is each half the size of the original? How do we get the subproblems? We chopped each X in half, right? We took the left digits and the right digits. So we have 4 subproblems of half the size, and we get a recurrence, right? Say the time to solve the problem is 4 times the size of solving half of the problem, plus the amount of work to put all the pieces together. So we use our master theorem. Use the master theorem with case of A equals 4, B equals 2, and C, which is the power of the N, is 1. And the master theorem tells us it's going to be N to the power of log 2 of 4. Log 2 of 4 is 2, right? Because 2 to the 2 is 4. So we get N squared. All right. How does that compare to the previous slide?
Same.
Same. So this is something that often happens in the analysis of algorithms, which is we try to do something, only to find that it's really no better than this simple approach, than the brute force approach. However, sometimes that creates an idea for something that's better. All right, so by the way, I have an example here, right? So you see we're taking a 2-digit number, a 2-digit number. We can think of that as 3 times 1 shifted, plus 3 times 6 shifted, plus 1 times 5 shifted, plus 6 times 5 with no shift. Okay, all right. So take a look at this. Okay, so a fellow by the name of Anatoly Karatsuba, this is 60 years ago, right, figured out that we don't actually have to have 4 subproblems in the divide and conquer. Okay, it looks like 4 subproblems, but he said we're going to think of it a little differently. And we're going to think of having 3 subproblems. One we're going to call Z of L, which is just equal to XL times YL. We're going to have Z of R, which is just XR YR. So those are 2 subproblems we already had, right? And then we're going to create another subproblem called ZM, which is this plus this. Now, if you look at it on the surface, it looks like, well, these are really 2 subproblems. So we still have 4, right? 1, 2, 3, and 4. But this is the brilliant part. He said, look at it carefully. This thing here is equal to this. Okay, so if you do the math and you multiply it out, you'll see that. Okay, how does that help? The answer is, but look at it more carefully. This subproblem we already have, right? This subproblem we already have. So how many subproblems do we have now? Well, we have an addition, but additions are easy. We have another addition, but additions are easy. So we have one big multiplication. So you have one big multiplication plus minus the 2 that we already have. So those are not extra work. So we now have 3 subproblems, even though it looks like they're 4 subproblems. So by being very clever, right, this is not something you or I would necessarily figure out on our own, but by being very clever, right, he figured out that we can think of these 4 subproblems as 3 subproblems. And now we go back to the same recurrence from before, and we say, let's replace that 4 with a 3. Replace the 4 with the 3. So now we have A equals 3, B equals 2, C equals 1. So we use the same case of the master theorem, n to the log 2 of 3, which is approximately n to the 1.6. Okay, so that is that's pretty remarkable. Let me say this: before this Karatsuba guy came up with this, no one believed that you could solve this in less than n squared. They assumed I got n digits in one number, n digits in the other number. It's going to take n squared. Period. End of story. Right? What do you mean it's going to be less than n squared? So this was a shock. Okay. Sometimes, you know, we expect something to happen, but we don't know exactly how it's going to happen. And sometimes we're surprised by the result. Okay, so this is one of those cases where we're surprised by the result. The computing community was surprised by the result. By the way, this is before we actually, you know, people were actually programming on computers for the most part. Okay, now we're going to do something very similar with matrix multiplication. All right, so here we have 2 matrices. I assume people are familiar with this from linear algebra or from discrete structures, right? Or maybe even Math 120, right? So these are matrices, and can someone tell me in plain English, how do I multiply 2 matrices by each other?
Isn't it like row by column?
Yeah, so I take a row of A and I multiply it by a column of B, okay? And I get an element. Okay, so here you see the formula for an element. So to get, you know, Cij, which is one element in the product, I do what's sometimes called a dot product, right? It's a row multiplied pairwise by a vector, right? So I'm taking, the first element in the row by the first element in the column, second element in the row by the second element in the column, and so on and so forth. I add that up and I get the number. All right, can anyone tell me how long does it take to multiply 2 matrices? So in this example here, how many operations, multiplication operations, would it take to multiply these 2 matrices? So let's be more specific, okay? How many multiplications are involved in computing this? just this one Cij? How many multiplications are in there?
M.
M as in Mary, right? Okay.
Yes.
Now, how many C's are there? So look at this matrix and someone tell me how many C's are in that matrix.
N times P.
N times P, correct. And if I take that N times P times the M, which is the amount of work to get each one, I have M and P. Okay, so that's in the general case. And the more specific case where the number of rows and columns are the same, and we call them all N, so the amount of work is N cubed. Okay, so generally speaking, when we talk about matrix multiplication, right, someone who, you know, knows a little bit about algorithms but hasn't, let's say, studied this particular topic in detail should be able to tell you, oh yeah, that's N cubed, right? Let's say if you took a linear algebra course and the professor said, you know, how long it'll take, probably told you it's N cubed. Okay, so what we're going to do now is we're going to say, but let's approach it from a divide and conquer perspective, right? We're going to break up our array into 4 quadrants. Okay, everyone know what I mean by a quadrant? We take it out and we divide it into 4 parts: the upper left, the upper right, the bottom left, and the bottom right. And we give them names, right? C11 is the upper left. Should I do that? I'll write that here. Okay. Oh, is this a screenshot here? Okay, that's an image. I can't comment it there. Okay, so again, this is the upper left, upper right, bottom left, bottom right. So we're going to take a divide and conquer approach. We say, let's break it up into, you know, chunks of rows, chunks of columns. We're going to cross multiply them, and we're going to do that. So take a look at this thing here and tell me how many sub problems do we have? Ignoring the addition, focusing on the multiplication of the matrices, of the sub matrices.
8.
8, right? I have 1 here, 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 1 here. I have 8 subproblems. And how big is each problem? Well, it's half the number of rows or half the number of columns, but it's basically, instead of being an n by n, it's an n over 2 by n over 2. Okay, so that's why I say n divided by 2. And how much work is involved? Well, I'm going to have to piece all things together, and we know that there are n squared elements in each one. So we assume that the work to put it all together is n squared. Okay, so we have a recurrence equation. What is our A in this recurrence equation? Using the master theorem, what's A stand for?
Number of operations.
I'm sorry?
Is it number of operations?
That's the number of subproblems. But what is that number here?
8.
8. Good. And what is our B here?
2.
Half.
Right. It's the size of the, you know, the fractional size of the subproblem. And then C is the power of the n in the work for dividing or putting our solutions together. So n squared will give us a C of 2. So we take log of B of A, which is log of 2 of 8, which is 3, which is bigger than the 2. So therefore solution, go back to your master theorem, is n to the log 2 of 8, which is n cubed. All right. So once again, if I use the, you know, algorithm from your linear algebra class, from your discrete structures, discrete math class, it's n cubed. I do a complicated divide and conquer. It's also n cubed. So once again, not so good. But along came a guy by the name of Strawson. Okay, this is more than almost 60 years old, 63 years old. Okay, and he said, same kind of idea as what we saw before. He said, take those 8 subproblems, and instead of 8, we're going to get 7 subproblems. We're going to call them M1, M2, up to M7. And then he shows you how to take those 4 quadrants of the product and to compute them based on these subproblems. So this is not something I would expect you to come up with on your own. It's not even something I need you to remember. Okay. What I do want you to remember is that what Strawson did is he came up with 7 subproblems instead of 8. And now our recurrence equation is going to be 7 times t of n divided by 2 plus O of n squared. So A is 7, B is 2, C is 2. Take log B of log 2 of 7, or log B of A is approximately 2.81. So our solution is O of n to the 2.81. So that is better than n cubed. Okay, it may not sound like such a big difference, but if n is big, that will make a difference. So here's a question for you in practice. Okay, if you had to do some matrix multiplication, what would you use? You had to write it yourself. Would you use this complicated thing, or would you use, the traditional algorithm from linear algebra? And the answer is, if your array is small, if your matrix is small, just use the traditional algorithm. If it's big, consider something like Strawson. How big is big? So depends really, but the estimate, the approximate threshold where it starts to be worthwhile is 50. Okay, so if your matrix is a 50 by 50 matrix that we're talking about, then you should really look into something like Strawson's algorithm. Okay, any questions on that? All right, so let's move on then. So our next problem, so we did Doomsday, we did some integer multiplication, some matrix multiplication. Now we're going to do exponentiation. So I want to find x to the n, right? I want to find 18 to the 100th power. So what do? Well, I multiply 18 by itself 100 times, and I will now have the answer to that. Probably my calculator will blow up, but okay, I have an answer, right? How many operations is that? How many operations?
An operation.
So it's n minus 1, okay? Because I need to multiply everything by the next, okay? So I need to do n minus 1, because the first term or the last term, depending on your perspective, I don't actually have to do multiplication. All right, so it sounds like if I want to find x to the n, I need to multiply x by itself n minus 1 times, right? Because 1 time is automatic, and that would be order of n. Can we do better than that? And the answer is yes. Okay, so first we're going to try something called decrease and conquer, where we say, okay, 18 to the 100th power is the same as 18 times 18 to the 99th power. So let's write a recurrence equation for that. So if I have only 1 term or 0 terms, the answer is I don't need to do any work. If in general, I need to do 1 operation for the multiplication plus solve the subproblem for 1 less. That's where this recurrence comes from. This recurrence is saying solve the subproblem for 1 less. And what's the solution to this? Anyone remember? At this point, you need to remember that. Not memorize, you should be able to derive it, but you should know that from linear search, minimum, a lot of algorithms have that. So it's order of n, and more exactly, it's n minus 1, right? Because the base case in this case is 0. So had it been, the base case been 1 equals 1, then it would have been n. But in this case, since the base case is 0, so it comes out to be n minus 1. All right, so that wasn't really very helpful, was it? But we're going to do a different approach. We're going to do a divide and conquer approach. And we say, listen, x to the n is equal to x to the n divided by 2 times x to the n divided by 2. Okay, so let's analyze that. So how many subproblems do we have?
2.
2, right? 1 subproblem and 1 subproblem. So here's our recurrence. Each subproblem is half the size. And then we have 1 operation to multiply these by each other, right? So we get n to the 0, n to the 0 is 1. And we use our master theorem. So a is 2, b is 2, c is 0. We get n to the log 2 of 2, which is O of n. So is that any better than this one here or that one there? We improve anything? We improve anything?
Yeah.
No, right? It was O of n before. Oh, I'm sorry, it's O of n now. It was O of n before, and it's O of n before. Okay. However, I want you to look back over here and tell me how many subproblems do we really have?
one since same.
Right, we have two sub-problems, but each sub-problem is the same. So if you're, little smart about it, you say, why should I redo the same work twice? Right? So with that in mind, what do? We say I have one sub-problem. My A is now 1. So I have A is 1, B is 2, C is 0. And I have actually a different case of the master theorem. So it comes out to be log base B of n, which is log of n. Okay, so by this, first of all, switching to divide and conquer, but number 2, by realizing that my two sub-problems are really the same sub-problem, right? I can get it down from order of n to log of n, or logarithmic time. Okay, so that's a cool little trick. Okay, next, any questions on that? Okay, next problem is evaluating polynomials. Okay, who can tell us what is a polynomial?
Like x to the power, I mean, n to the power of something.
Okay, so polynomial has a variable. Sometimes it can have more than one variable, but we're going to keep it simple with one variable polynomial. And the variable can have powers, right? So powers. And it can also have coefficients. In general, the coefficients of the different powers are not necessarily the same. So this is the generic form for a polynomial of degree n, right? The highest power is n for one variable. Okay, so how do you evaluate this? Let's say I told you x equal, I gave you your a, the a's, and I told you x equals 3. So how would you evaluate that? So you would say, okay, so I take my a0 multiplied by 3. I take 3 to the first power multiplied by a1, 3 to the second power multiplied by a2, 3 to the n minus 1 power multiplied by an minus 1, 3 to the nth power multiplied by that. Okay, so how much work is involved? So let's go through it term by term. And I'm going to start at the bottom because the bottom is easier. So how much work was involved in multiplying one coefficient by x to the 0? So what is x to the 0?
1.
1. So I don't really need to do any work because I know that that's just going to be 1, right? What about this? How much work is involved in multiplying coefficient a1 times x to the 1?
1.
1. And the next one, which you don't really see here, is a2 times x to the 2. How much work is involved there?
2.
2. Right, so keep going all the way up to the top. So in this case, I need n minus 1 operations to do the x to the n. One more operation to multiply by the coefficient, I get n multiplications. So if I add all that up, 0 plus 1 plus 2 plus 3 plus 4, all the way up to n, what do I get?
N times n plus 1 over 2.
N times n plus 1 divided by 2, right? That's from Gauss. Okay, so I get that. And what order of magnitude is that? What do we call that? What kind of function is that?
N squared.
That is n squared. And what other name do we have for n squared?
Quadratic.
Quadratic, correct. Okay, so, okay, quadratic time. The question is, can we do better than that? And the answer is we can. We use something called Horner's method. Okay, take a look at when Horner lived. He lived a long time ago, before there were any kind of computers. Not even sure what electricity looked like.
Good, Professor.
Yeah,
You go back one slide.
yep.
So when, like, let's say evaluating an times x to the n, shouldn't that be log n multiplications? Because we showed last time we could do x.
Ah, okay, so that's the right kind of thinking. The right kind of thinking is say, can we use something, an improvement that we made before in this context? So the answer is you can. The answer is you can. Right now, this is a brute force approach. So we're not, we're saying, if you didn't know, if I gave you this problem and you had not taken today's lecture and I said, how many multiplications are going to involve, what would you come up with?
Okay.
So I agree with that's the right kind of thinking for this course is, hey, wait a second. we learned, an improvement we can make, but this is brute force, right? If you implemented this the way most people would implement this, you took intro to programming, you know how to write a Java program or C++ program or Python program, and I said, evaluate this, you would probably just call the exponent function and you probably wouldn't realize what's going on behind the scenes, but yeah. Okay, so what George Horner did, okay, by the way, just to run with that idea, so if we did use the improvement, what would it take?
N log n.
Take n log n. Okay, so keep that in mind. All right, so what this Horner guy did, okay, this is over 200 years ago, he said we can rewrite this. Okay, we can factor out the x's and factor out x and factor out x. Okay, keep on going, right? Everyone see that, right? So if I take an x out, I get all this, and then I take another x out, I get this, and so on and so forth. So he says, and the innermost point of this, I'm going to have to do one multiplication. Then one layer of parentheses out, I have to do another multiplication. Another layer of parentheses out, I do another multiplication, right? At each layer of parentheses, I have to do one more multiplication. So how many multiplications am I doing?
And multiplications.
And multiplications, okay? And multiplications and one more addition. Okay, so I'm working from the inside out. So how long does that take?
O of n.
O of n. All right, so that's O of n, by the way. By the way, you don't even need recursion for this. So it's also, it's better because there's actually a lot of work, when we did the exponentiation, there's a lot of work in actually figuring out what those exponents ought to be and so on. So it's not as, it's still log of n, but it's not as simple as we made it out to look. All right, so this is order n, very, very actually simple to implement. Okay, this is not hard to do. Fine, right? So you imagine that you had a list of, the coefficients. Okay, and here I have a worked out example. So again, I want you to see the x's being factored out, right? So here, no x's are factored out. Here I have one x factored out. You have another x factored out, another x factored out, and you see the work that is being done. Okay, we have one or two more topics here. So what about square root, right? We want to devote equal time. So we did exponentiation, which is powers. And now well, I guess it's a kind of power also, but it's a fractional power, right? Square root. Okay, so how do we compute the square root? So we do brute force, right? We just keep on checking numbers until we exceed the number, then we know we have a square root. So for example, if I want to find the square root of 100, and I don't know that it's 10, so I say, well, let's try 1. 1 squared is less than 100. 2 squared, less than 100, 3 squared, less than 100, 4 squared, less than 100, 5 squared, less than 100. I go up to 10, I get 100. Okay, now I might not be so lucky to get, perfect integer. Let's say I wanted the square root of 95. So I try 9, I get 81. I try 10, I get 100. Oh, I know that it's somewhere between, 9 and 10. Okay, and fine. So that's like a brute force approach. And the time takes is, well, assuming it's an integer, if it is an integer. So I just keep going one by one, and it's going to take the square root of n. Okay, so we're going to do something a little better here. Okay, we're going to say, let's do a binary search kind of approach, right? I know my number is between something and something else. Okay, the worst it could be is 100, right? Because a number is not going to be, it's less than, if it's bigger than 1, it's not going to be, the square root is not going to be less than the number itself. So I'm sorry, it's not going to be more than the number. So I know that my number is somewhere between 1 and n. So I take the average, n over 2. Okay, n over 2, I square it, it's bigger than my number. So I take n over 4. And I keep on, finding the midpoint. Just like in binary search, you keep finding the midpoint, and you see, is it higher or lower? So I do that here as well. Okay, so you see a worked out example, right? You can see when I probably created this example back in 2020. So we took the, we got a quick upper bound, right? So we don't really know what the answer is, but we said, listen, it's not going to be more than 50, right? So do that, and then you get another lower bound, and you get the midpoints, and so on and so forth. All right. And sooner or later, you get to an answer, all right? Okay, so here's your code for that. Does it make sense? Right, so again, we're using a binary search approach. We get an upper bound, a lower bound. In this case, we simplified a little bit. We said the lower bound is less than, it can't be more than 4. It's not less than 40, not more than 50. Strictly speaking, you would start with a lower bound of 1 and an upper bound of n, which in this case is 2020. Probably just wanted to fit it on the page so we would get a number. But you see, we get pretty good precision, right? In just a few iterations, we have pretty good precision here, right? To it looks like at least 4 digits. Okay, so here is the code for the binary search approach to finding a square root. And do we have a time complexity here? Yeah, the time complexity is log of n, not unlike the binary search for searching. But now we have another approach. This is called the Newton-Raphson method. Anyone? How many people here have taken linear algebra? A lot? Okay, I see some hands there. So here is another question. Let me put my chat box on. Has anyone seen the Newton-Raphson method before?
No.
Any yeses there? Either in linear algebra, or maybe if you took a course in like numerical methods or numerical, nope. Okay, so we start with an estimate. Okay. Now, this is sort of a funny kind of estimate because the whole point is to get the square root. But let's say it's a number that doesn't really have a, yeah, maybe I shouldn't say that. Let's just fix that. So let's say we start with an estimate of square root of n, right? So usually we can get a reasonable estimate. And then what we're doing is we compute each number in terms of the previous estimate as well as n over the previous estimate divided by 2. Okay, so I picked 323 as my example because this is CS 323. And we estimate at 220. Now we know that 20 is not going to be the right answer, but we know it's in the right ballpark, as a reasonable starting point, because 20 squared is 400. So, okay, it's good. Then we take 20 plus the 323 divided by 20 divided by 2. This is 18075. We take the 18075 plus the 323 divided by the 18075 divided by 2. We get 17972. And you can see we're already getting really close, right? You see, another iteration doesn't really add very much precision anymore, right? So the time complexity is log of n, which is really fast, okay? So again, we had 3 algorithms. Algorithm number 1 was order n. Algorithm number 2, and by the way, can't really be used that effectively for these, precision, finer precision. And then we had log of n using the binary search approach, and then this with this Babylonian method, which is an old method, but it's named after, Newton is the famous Sir Isaac Newton, right? So that is log of n, which is really, really nice and fast.
So how did you generate the estimate in the beginning? Like, how'd you get 20?
How'd I get 20? So again, we're taking a rough number, right? So we're saying, okay, I don't really know what the number in the square root of 323 is, but I know that, 400 is,
Well, I mean, I know that you know that, but like, how would you code for that?
How would you code for that? How would you code for that without? So, okay, so if you don't really have an estimate, in other words, you're not allowed to sort of use any heuristics. So you could just use the 323. Here, I think this is the last slide. Let me just see. This is the last slide. It's the last slide. So, okay, so here's what we're going to do here. We have 3 minutes left. Let's open a Google Sheet. So I want to show you. Okay, so here's our estimate. Okay, so let's just say we don't know what it is. So we're going to use 323. Okay, so we take the number itself. Okay, so that's a really poor estimate because obviously it's nothing near there. And then we said you're going to take your number in A1 plus the number itself. So what is our N? Well, let's do this. Okay, so this is going to be our N. So our N is 323. And to Ellie's point, let's say we're not allowed to be smart about our estimate. So we're just going to take as our initial, we're just going to use that. Okay. And then we're going to do this. So we're going to say it's equal to A2 plus our N, which is A1 divided by A2 divided by 2. Okay. And then this is going to be our B. So we go over here and we say that's equal to B2. Okay, and we pull that down. Okay. Okay, so it's basically around here where we get it. Now for 323, 8 operations isn't so impressive, but let's take a big number, right? Where we start to appreciate the difference, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so how many operations is it taking to? Okay, so at this point already, right, we basically have the answer, right? How many operations would it have taken? Again, this is with a really bad estimate, starting estimate. Okay, but we could do something else, right? You could just take half of it or a quarter of it, right?
Yeah.
Right. So we know it's going to be fraction of it. And remember, if we're too low in our estimate, we can always, it'll just go in the other direction, right? There's no rule that you have to come from the top. So we could say, let's take a quarter of that, right? So we're going to, zero in a little bit closer. Okay, so, there are probably some heuristics that we would agree upon, that don't have to take additional operations. Like anything else, so we have to stop here, but like anything else, the takeaway here is, the improved algorithms don't usually give us an improvement for small cases. They tend to be valuable for larger numbers. Okay, so in algorithms in general for larger sizes, right? So you're not going to use, it's not worth using quicksort for 5 elements. You'll use insertion sort for 5 elements. So you start to see the improvements on these things when your N is big, or in this case, our N is, the size of the number. Okay, so we're going to stop here. Everyone remember the top hat? What's our top hat code for today?
7915.
7915.
Professor, I have a question.
Yes, please.
Was assignment 1 graded? Because on top hat, it says as a 0 out of 10.
For this class, it was graded. So there are 2 possibilities. Either it wasn't submitted or I missed it. Okay, so if you did submit it, if you could just in Slack tell me the date and time when you submitted it, and I'll go back and I'll look for it. So generally for all the students, I did a search on the directory for their name if it didn't come up in the spreadsheet. But it is possible that I missed it.
Okay, so just send you the
So
data.
send me a message in Slack saying I got a 0 on assignment 1. I submitted it at this date and time. Please check again, and I will check again.
Thank you.
Okay? All right. All right. Okay, so that is it for today. All right. Everyone have a good day. Bye-bye.
Bye, Professor.
Hi, Nubia.